Hello class, welcome to the Stat 511 Week 5 video on sampling distributions. In this video, we're going to cover 5 main objectives. First, we want to understand the concept of sampling distributions. Second, we want to specify the sampling distribution for our sample mean. Third, we're going to learn about the central limit theorem, which we often abbreviate as CLT. Then we will use the central limit theorem to find probabilities about our sample mean. And then finally, we're going to focus on a few other sampling distributions. Let's get started with our first objective. Just a quick review of what is a population versus a sample. So recall that a population is the complete set of people or things being studied, but the sample is the set of people or things from which data are actually being obtained. And so a sample is a subset of our population and hopefully covers our population in brief. So for us, our population for a random style, let us know that each observation in a population is a random variable x that takes on values according to some probability distribution f of x. We established this in our previous lecture. When we refer to a normal population or a binomial population or the population f of x, we mean a population whose observations are values of a random variable having a normal distribution or binomial distribution or probability distribution f of x. In other words, whatever probability distribution we're examining. So to state that a little more clearly, when we refer to, we'll just use the normal population. When we refer to a normal population, we mean a population whose observations are values of a random variable having a normal distribution. And this also applies for any other distribution. So let's think about a sample in that same scope of things. In selecting a random sample of size n from a population f of x, we're going to define that random variable xi, where I equals 1 to n, to represent the ith measurement or sample value we observe. Random variables x1, x2, all the way to xn constitute a random sample from the population f of x, with numerical values x1, x2, all the way to xn. Notice how it is denoted differently when we are talking about the random variable, it's capital X, and when we're talking about the numerical values, it's lowercase x. x1, x2, all the way to xn are independent with the same probability distribution f of x. So using our understanding of probability rules, particularly those that pertain to independence, then we can say f of x1, x2, all the way to xn is equivalent to f of x1 multiplied by f of x2 multiplied by dot, 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 all the way to f of xn. We may also recall what our sample mean is, since that's going to be the focus of our first sampling distribution. So we let x1, x2, all the way to xn represent n random variables. So therefore our sample mean, denoted by x bar, equals 1 over n multiplied by the summation of I equals 1 to n of xi. And our sample mean statistic assumes that the value of lowercase x bar equals the equals 1 over n multiplied by the summation of I equals 1 to n of xi, when capital X1 equals lowercase x1, and so on for all of the xi's. And so when we say sample mean, this is going to refer to both the statistic and the computed value. So let's start talking about estimating our population mean mu, and this really gives us a good understanding of what is a sampling distribution as we really get into it. So let's say we take one sample from our probability distribution f of x. And so we consider the sample mean, and we'll call that x1 bar. Notice that on this horizontal line, I have an arrow pointing to the center, and we're going to have that center spot be where the true population mean mu actually lies. And so we can see that our x1 bar is actually a little bit to the left. So it's not exactly at the population mean mu. But we can kind of, we'll say, fix that because our statistic, our sample mean, is a random variable. So it can take on different values depending on the specific sample taken from the population f of x. So suppose we take 4 more samples so that we have x2 bar, x3 bar, x4 bar, and x5 bar. And we can see that twice we had a sample mean pretty much be exactly at the true population mean, once where it was a little bit above and twice where it was a little bit below. If we consider then adding even more samples so that at this point we have, looks like 13, then what we can see is that we have computed values occur according to some probability distribution as we add more samples in. And once again, we can see that most of our values are clustering around the true population mean, with some values being a little bit above, a little bit below, but most are being somewhere close to our true population mean. And this is the concept behind sampling distributions. So let's take a look at another motivating example to really get an idea of this. So suppose that we have data from all 3,945,102 live births in the United States in 1998. So one variable, which would be our birth weight in grams, and we can see that along our x-axis. Along the y-axis, we see the number of births. Our mean in this case is 3,318.8 grams with a standard deviation of 609.5 grams. Now, if we were to take a sampling distribution of that or a sample of that, so we're going to examine 10,000 samples of size 100. And for each of these, we calculated our sample mean for each sample. In this case, we could see that the average of our 10,000 mean was 3,318.9 grams, and we had a standard deviation of 60.8. So if I flip back, what we could see when we compare to the true population versus our sampling, we had a similar mean, but our standard deviations were not quite the same. And that is generally what occurs when we have a sampling distribution, is that what we'll notice is that our population mean will stay the same, whether we have the true population information, which honestly we rarely have, versus the sampling distribution. The means will stay the same, but there is a disconnect with the variances. And that's based on the change in sample size. So now that we've kind of sort of gotten a little bit of a kind of background understanding of sampling distributions, let's start defining it formally. So let us suppose that we simulate random samples from a known population. For each of those, we compute the sample statistic, the sample mean, for each of the generated samples. The statistic, x bar, our sample mean, is a random variable and thus will have its probability distribution. This distribution is called the sampling distribution. We want the sampling distribution to be centered at R mu, and we're going to want that variability to be as small as possible. So let us consider the population f of x with mean mu and variance sigma squared. If a random sample of size n is taken, and our sample mean is computed, then what we expect to occur is that the mean of our random sample is going to be equivalent to the population mean, and that the variance is going to be equivalent to the population variance divided by the sample size we have. So if you think back to our earlier example when we were comparing the live births, I said that we noticed that the population mean stayed the same, but what changed was the standard deviation. And what occurred in that case is the formulas we see here, which for standard deviation would be the population standard deviation divided by the square root of our sample size. So for a sampling distribution of our sample mean, which will follow our normal population, when taking samples of any size n from a normal population with mean mu and standard deviation sigma, our sample mean will follow the normal distribution with mean mu and variance, or excuse me, standard deviation of the population standard deviation divided by the square root of n. And that is only if our x follows the normal distribution with mean mu and standard deviation sigma. And then in that case, our statistic, our sample mean, takes on values that also follow a normal distribution, again with mean, mu, and standard deviation equal to sigma divided by the square root of n. And this is going to be true for any value of n. And so with using this concept, we can do something called the central limit theorem. And of all the theorems and information you are going to learn in statistics, one of the most important really is the central limit theorem because it is applied so frequently. So, what is the central limit theorem? When we take large samples of size n from any population f of x with mean mu and standard deviation sigma, then our sample mean is going to approximately follow the normal distribution with mean mu and standard deviation of sigma divided by the square root of n. And so that is if x has any distribution with a mean mu and a standard deviation sigma, then our statistic, the sample mean, is going to take on values that follow an approximate normal distribution with mean mu and standard deviation sigma divided by the square root of n when n is large. And this is really very important. What this says is, so if we have some scenario that says that follows, say, the binomial distribution, which is that very, black and white, we've had success or failure. If we have a sufficiently large sample, that sample is going to follow the normal distribution, which, as we established in our previous lecture, the normal distribution really does have some really nice properties. And using the central limit theorem, we can apply those properties. So to kind of give an idea of how the central limit theorem works visually, because I know it may not be naturally intuitive, let's take a look at a distribution of the population of CEO salaries, and we can notice that this is highly skewed. But if we now take a sampling distribution of x bar when n equals 10 with the results of 1,000 samples, we can see that while the distribution is still skewed, it isn't as skewed as in our first case. We do it again, this time with a sample size of 50 for 1,000 samples. Notice that still a little bit skewed, but even less skewed than before. Again, now this time we have a sample size of 100 from that 1,000 samples. And you can see that this almost looks like it's normal. And I would say at this point is actually approximately normal. And honestly, that is exactly what occurs. as that sample size gets larger, even if we're originally looking at something that is skewed, it becomes normal. So this may bring you to a very logical question of, okay, we say that when n is large, it can approximately follow the normal distribution, but how do we know how large of an n are we going to need to use? Many textbooks use the value of 30. Some use 25. Generally, 30 is the main standard that is used. Um, Truthfully, it really does matter how skewed the distribution is before it becomes normal, but 30 is kind of the standard value that's used in lack of a concrete. I do want to say a big warning. Um, just a large N does not imply that the population somehow becomes normal. It just appears. If the population was not normal to start with, taking a large sample from it will not change that. It's that the distribution of the sample mean is approximately normal. Okay, so this brings us to our fourth objective, and that is to use our central limit theorem to find probabilities about our sample mean. And a lot of this is going to be practice problems. In fact, the grand majority of it is. And these practice problems are really just a nice extension of what we did in the previous lecture when we were finding probabilities with the normal distribution. We just have to apply our concept of our sampling distribution and our central limit theorem. So let's take a look at a first example. So shower times are normally distributed with a mean of 11.4 minutes and a standard deviation of 2.7 minutes. A hot water system is adequate for 81 guests if the mean shower time is less than 12 minutes. A hotel currently has 81 guests. What is the probability that there will not be enough hot water? So taking a look at our example, we have that X follows the normal population or normal distribution with a mean of 11.4 and a standard deviation of 2.7. And we are given that we have a sample size of 81. And we are asked to find the probability that our sample mean is less than 12 minutes. While using our central limit theorem, we do need to adjust our information. So we know using our central limit theorem that the sample mean then is going to approximately follow the normal distribution with a mean of 11.4 and a standard deviation of our population standard deviation, which is 2.7, divided by the square root of our sample size, which in this case is 81. And so that's going to equal a mean of 11.4 and a standard deviation of 0.3. And that honestly right there is the only real difference to the problems we were solving in the previous lecture. Now we can go ahead using our knowledge of z-score to find the probability of not having the enough hot water. Excuse me, and I just realized I made a typo. This should have been greater than. Okay, but jumping back into our z-score, so we were talking about having greater than 12, plugging in our mean, because we can recall, so actually I'll erase again. Remember, z is equal to x minus mu divided by sigma. X in this case is 12 minus our mu of 11.4 divided by our sigma of 0.3. and this will give us a z equal to 2. So therefore, to find the probability of our sample mean being greater than 12, this is going to be equivalent to the probability of z being greater than 12. Again, this comes directly from our z-score. And because our z-table gives us area to the left of the curve, we'll have to rearrange this formula to be 1 minus the probability of z less than 2. And now we can look up our value in the standard normal distribution table. And so we're going to look for when z is 2. And 2.00, we are going to have a probability of 0.9772. So going back to our slides, so this will be 1 minus 0.9772, or in other words, this would become 0.0228. So therefore, we can say that we have a 2.8% chance of running out of hot water. And as we can see, this is really not too bad to solve. The central limit theorem really just has us adjust information from the population or in order to reflect the sample size and the situation that we're looking at. So let's take a look at a second example. So suppose for a particular community, it is known that the mean amount of water used per home during October is 1,250 gallons, and the standard deviation is 325 gallons. The distribution for amount of water used is skewed to the right. Now, in this case, we are going to let X equal the gallons of water used per home. And we know that X is skewed right with a mean of 1,250 and a standard deviation of 325. Now, as our N, our sample size is large, in this case it's 50, that means the central limit theorem will apply. So for us, that means that our sample mean will be approximately following the normal distribution with a mean of 1,250 and a standard deviation of 325 divided by the square root of 50, which if we simplify, that means we'll have a mean of 1,250 and a standard deviation of 45.96. So now we are going to ask the question, what is the probability that the sample mean amount of water used is less than 1,100 gallons? And again, we can recall from our previous slide that our sample mean is going to follow the approximate normal distribution with mean 1,250 and a standard deviation of 45.96. So as we want to find the probability of our sample mean being less than 1,100, we can use our knowledge of z-score, where z is going to be 1,100 minus 1,250 divided by 45.96. This will give us a z-score of negative 3.26. So we are going to really be trying to find the probability of z less than negative 3.296. Using our z-table, we can go ahead and find negative 3.29, negative 3.26. So negative 3.2 and to 6, so that's going to give us a probability of 0.0006. Going back to our slides, So this means the probability of z less than negative 3.26 is 0.0006. So therefore, for us, that means we have a 0.06% chance of our sample mean being less than 1,100 gallons, which for us that would clearly be a very small percentage and unlikely to occur. So let's take a look at a third example because why not? More practice is better. The radio station can afford to pay for a total of 69,000 gallons. What is the probability that the total number of gallons for a random sample of 50 homes will exceed the 69,000 gallons? So, still using that information from the previous slide, we want to know what is the probability that the total is greater than 69,000. Using our knowledge of our sampling distribution, that means we're really asking what is the probability of our sample mean being greater than the 69,000 divided by 50, because we're going to divide it up into each home to make things a little bit easier given the information we had on the previous slide. And so really what we're going to find is what is the probability that the sample mean is greater than 1,380. Using our knowledge of z-score, we'll plug in, and for x we have 1,380, for mu 1,250 divided by our standard deviation of 45.96. That's going to give us a z-score of 2.83. Plugging in, wanting to find the probability of our sample mean being greater than 1,380, we can use our z-score to find the probability of z being greater than 2.83, which is equal to 1 minus the probability of z less than 2.83, which would be equal to 1 minus 0.9977. We get that from the z table, which will equal 0.0023, or in other words, 0.23%. So the probability of our total being greater than the 69,000 gallons would be 0.23%, which we can see is pretty rare. So in both our example 2 and example 3, we had these situations that are pretty rare. And I want to talk about what that can mean for us. So let us suppose that that total did exceed the 69,000 gallons. So therefore, our sample mean was greater than 1,380 for each house. And again, we are still assuming that our population mean is 1,250 in this scenario. And so having the situation where our sample mean was truly greater than 1,380, while we are assuming that the true population mean of 1,250, that situation occurring is either extremely rare, because we're looking at it, 0.0023 is an extremely rare event of this to occur, or if this did occur, what it could imply is that this population mean of 1,250 isn't really true anymore. It may be old data, and so therefore we're operating under a false assumption. And so what happens when this very rare event occurs is we generally consider this to be an evidence against our assumption. So specifically in our example, there was only a 0.23% chance of taking a sample that resulted in a sample mean value of being greater than 1,380 if our true mean really is the 1,250. So in such calculations, if there is less than a 5% chance of an event occurring and we have it occur, we consider this to be strong evidence against the assumed value of our parameter of interest. So basically, to say that more clearly using the context of our example, if our calculated probability is less than 5%, then we generally consider that to be evidence that this true population mean isn't accurate. It didn't actually, the information we have isn't accurate. And this concept is very important for us because the second half of this class focuses on the idea of confidence intervals and hypothesis testing. And this concept that we've introduced in this slide and the previous slide forms the basis of hypothesis testing. It's the idea of what happens when we get an event that is super rare and it is therefore evidence that our previous assumptions are no longer accurate. But that is something we are going to focus on later in this course. Like I said, it is a large focus of the second half of this course. So it's something I wanted you to be aware of, particularly because I know sometimes with so much information being thrown at you, kind of getting a synthesis of the large picture is difficult. And so those two previous slides really were my attempt to have you understand how everything's kind of connecting and where things are going forward. So far in this slide, we've really been focusing, or slide, this lecture, we've really been focusing on the sampling distribution of the mean. For the remainder of this lecture, we are going to focus on other sampling distributions. I'm not going to spend as much time as I did on the sampling distribution of the mean. They are all generally pretty similar. It's kind of the same idea that we had in the sampling distribution of mean, but the formulas can be a bit different. So for us, we're really going to focus on four other sampling distributions. First, we're going to focus on the sampling distribution for a proportion. Then we will focus on the sampling distribution of our sample variance. And then we'll finish off talking about t-distributions and f-distributions. So we can recall that the probability of success P for the entire population may be determined by the number of successes in the population over the total number in the population. So until now, we've been finding the probability associated with individuals randomly selected from the population. Now we're going to be focusing on finding probabilities associated with the sample statistics from randomly selecting a group from the population. So for us, the sampling distribution of a proportion is when we take samples of a sufficiently large sample size n from a normal population with mean p and standard deviation square root of pq over n, and we'll say that our sample proportion p hat is going to approximately follow the normal distribution with mean p and standard deviation square root of pq over n. And again, this is assuming, or that is if p itself does follow the normal distribution. And so at that point, then our statistic p hat takes on values that will follow the normal distribution, with our mean being p and our standard deviation being the square root of pq over n. And this is going to be true for any value of n where both np and nq are greater than 5. And recall q is 1 minus p. So if p is 5, then q is 95, or rather 0.5 and 0.95. And to have this visualization idea of pulling entire samples, so let this blue circle be the entire population. And what we do in order to get our P1 hat, P2 hat, P3 hat, and P4 hat is we take whole samples from the population to represent the entire population. So let's take a look at our first example. According to Coca-Cola, 60% of the US prefers Coke over Pepsi. What is the distribution of the proportion of people who prefer Coke over Pepsi from a random sample of 40 people from the US? Oops, looks like I made a typo in the sense that I copied the same slide twice. Oops. All right, so um, P hat is going to be approximately normal with mean P and standard deviation of PQ over N, or rather the square root of PQ over N. So plugging in, that means that P hat is going to approximately follow the normal distribution with a mean of 0.6 and a standard deviation of the square root of 0.6 times 0.4 all over 40. Simplifying, that means P hat is going to approximately follow the normal distribution with mean of 0.6 and a standard deviation of 0.07746. So far, again, very similar to what we did when we were doing a sample distribution for the sample mean. The means stay the same, the standard deviations change a bit. So what are some of the properties of the distribution of P hat? Well, so first, since P hat follows the normal distribution, it does take on all the properties of the normal distribution, meaning that it is symmetric, unimodal, and centered at P, which is our population proportion. We can find and use z-scores, which is exactly what we're going to do. And so for us, we can remember that our z-score is our observation minus the population mean divided by the population standard deviation, which in this case, applying it for proportions, this is going to be p hat minus p divided by the square root of p, or excuse me, yeah, divided by the square root of pq over n. And we can also use applications of the 68, 95, 99.7 rule. So still continuing our example 1. So from our Coca-Cola example, what is the probability that the proportion of people who choose Coke over Pepsi from a random sample of 40 people will be above 65% or 0.65? So for us, we established in the previous slide that P hat approximately follows the normal distribution with mean of 0.6 and a standard deviation of 0.07746. Plugging into our z-score formula, z equals 0.65 minus 0.6, all divided by 0.07746. So this is going to give us a z-score of 0.645. Now that everything else becomes old hat, we want to find the probability of P hat being greater than 0.65, again, because we want to find above 0.65. Plugging in our z-score value, we have the probability of z being greater than 0.645. Using our z-table, we know that we don't have areas to the right of the curve, only left, so that will have to become 1 minus the probability of z less than 0.645. And then from our z-table, we can see that that's going to be 0.2595. So going back to our question, what is the probability that the proportion of people who choose Coke over Pepsi will be above 65% when it's a sample of 40 people? The answer, 25.95%. So asking another question, what is the probability that less than 57% of a random sample of 40 people will choose Coke over Pepsi? Well, again, we know that the P hat approximately follows the normal distribution with mean of 0.6 and a standard deviation of 0.07746. Plugging in for our z-score, that would be 0.57 minus 0.6 over 0.07746. So this will give us a z-score of negative 0.39. Then, as I said before, it's old hat. We'll do the probability of p hat less than or equal to 0.57, which will equal the probability of z less than negative 0.38. Using our z table, we'll get a probability of 0.3483. And so that's pretty much what we need to know about the sampling distribution of proportion. The last little bit we want to consider is when is it appropriate to apply this? And so it's safe to use the normal distribution to describe the sampling distribution of p hat when the following conditions are met. So first, we do need to have the success failure condition, which says that our NP and NQ need to be greater than or equal to 10, so meaning we need to have more than 10 successes and 10 failures. We also need to have this 10% condition, which is where our sample size is less than 10% of our population. And finally, we do need to have samples that are independently and randomly chosen. And so we can ask if our conditions are met. So considering this example, a cop estimates that 60% of people on a particular highway are speeding, so they may decide to park and radar to monitor how many cars are speeding out of the first 50 cars that pass them. Are the conditions met to apply the normal distribution? Is our success failure condition met? Well, let us consider. If we have 50 cars and our standard is 60%, 60% of 50 is greater than 10, yes. And on the opposite end is 40% of 50 more than 10, and yes, that's true as well. And what about the 10% condition? We are examining the first 50 cars that pass, and I will say that given that it is a highway, I think that it's safe to assume that 50 cars is less than 10% of the population. And then the next part of the question is randomization. This is the condition I personally have problems with in this case, examining the first 50 cars that pass them. If we're considering rush hour when we're in bumper to bumper traffic, we're not going to get an accurate image of what is this a number of people who are speeding at, say, 3 o'clock in the morning when no one else is around. So I personally feel that the randomization condition was not met in that case. So let's consider another one. A bank estimates that 5% of people default on their loan payments if the bank uses a random sample of 80 customers. Is it appropriate to use the normal distribution to describe p hat, the sample proportion of people that default on their loan payments? Well, so let's examine 10% condition. I will say, so I'm considering 80 customers, not knowing the true population of how many people have loans at the bank and what bank it is. So, for example, if we're talking a large bank like PNC, then obviously more than 80, significantly more than 80 customers have a loan. So that would be appropriate to consider. Randomization, we are told that it is a random sample, so that is very good. Now we have our success failure condition. So we do need to consider that we are looking at 5%, and so we need to have at least 10 people. And so if we consider 5% of 80, that's actually only 4. And so that means that condition's not going to be met. Remember, we need to have our NP being greater than or equal to 10. Our N in this case is 80, and our P is 5%, and that equals 4. And 4 is definitely not greater than or equal to 10. So therefore, our conditions are not met in this situation. So the central limit theorem is not going to apply. So let's now take a look at a second example. According to the National Assessment, 22% of women have a BMI that is above the healthy mark of 25. A random sample of 200 women were selected and 31 of them had a BMI higher than 25. Would we consider this to be an unusual result? Now, first off, checking our assumptions. We were told that we have a random sample of 200 people, 200 women. I think it's pretty safe to say that we're going to have a random sample, so therefore our condition of randomization has been met. Our 10% condition of 200 women, 22%, that would be 44 women, and then obviously the opposite n of 1 minus the 0.22 would also clearly give us a sufficiently large failure rate. And then so that would be our 10% condition being met, or excuse me, rather our success failure condition being met. As far as our 10% condition, I think it is pretty safe to say that 200 women is less than 10% of the entire population of women in the US. So at this point, then we can actually move forward and solve the problem using the central limit theorem for proportions. So we've checked our conditions. So now we can actually go ahead, as I said before, solve our problem. We're going to find our z-score and probability. So in this case, our p hat is going to be 31 over 200, which is equal to 0.155. Our expected mean is going to be 0.22, and our standard deviation would be 0.22 times 0.78. Remember, it's 1 minus 0.22 divided by 200, which is going to give us a standard deviation of 0.029. Plugging in for our z-score, then we will have z equal to 0.155 minus 0.22, all divided by 0.029, which will give us a z-score of negative 2.24. And again, we were asked to find we wanted to know, let's see, according to the National Assessment, 22% of women have a BMI that is above the healthy mark of 25. A random sample of 200 women were selected and 31 of them had higher than 25, and we wanted to know if that was unusual. And so using our z-score, we found the probability of z being less than negative 2.24, and we got a probability of 0.0125, which would be 1.25%. And as we established in the previous slides, we consider anything less than 5% to be unusual. So yes, I would say that that is unusual. And so that actually was pretty much all I want to talk about as far as the sampling distribution of p hat goes. It is very similar to this sampling distribution of the sample mean. So this leads us to want to talk about the sampling distribution of our sample variance. So earlier we established that we consider x bar to be a statistic, and our x bar has a distribution, and if a sample of size n has taken from a normal population with mean mu and a standard deviation sigma, then our sampling mean x bar is going to approximately follow the normal distribution with mean mu and standard deviation sigma divided by the square root of n. And I do want to apologize. You'll hear me often want to say mean mu and variance instead of standard deviation. That's something that gets changed quite a bit depending on the textbook and even sometimes your professor. Some textbooks strictly say mean and variance, others use mean and standard deviation. And so that's why you're going to hear me switch a lot, because I'm so used to having to go back and forth that I often get them mixed up. And honestly, we know how closely related the standard deviation variance are. It's not a stretch. So continuing in talking about the sampling distribution of our sample variance, our sample variance S squared is also a statistic, and it estimates the population variance sigma squared. So for us, a useful fact to know is that our sample variance is the variance of a random sample of size n taken from a normal population with a variance sigma squared. So this gives us a statistic of chi squared equal to the quantity of n minus 1 and quantity of our sample variance over our population variance. And it follows the chi-squared distribution with degrees of freedom n minus 1. And in our case, this would give us a mean equivalent to our degrees of freedom and a variance equivalent to 2 multiplied by our degrees of freedom. And the chi-square distribution is not one you're probably familiar with. In this slide, we do have an image of it. Notice it is unimodal, but it is skewed. And I will tell you that the exact shape and curve is determined by the degrees of freedom. So the chi-square distribution isn't necessarily a single distribution, but a series of distributions that is determined by its degrees of freedom. And we have chi-squared alpha, which represents the chi-squared value above which we find the area alpha, which for us, this is kind of where we have our rejection region, or it's that cutoff point for us where we consider an event to be unusual or not. So just as there is a binomial table, Poisson table, and normal table, there is also a chi-square table which we can use for a chi-square distribution with 4 degrees of freedom. The area greater than our chi-squared of 11.143 is 0.025, which you can get from your table. And for a chi-squared distribution with 4 degrees of freedom, the area greater than chi-squared equal to 0.484 is 0.975. And so 95% of our area is going to be between 0.484 and 11.143. And so as far as detecting unreasonable values, so if you take a sample and calculate a chi-square value for a chi-square distribution with, say, 4 degrees of freedom, you should expect that your sample results in a value between 0.484 and 11.143 95% of the time. If your value is outside that range, then we would start to consider this to be an unreasonable value, or that there's an issue with the assumptions that you used, meaning that the population variance that you were given or you assume to be true may not be actually true or may not be reasonable. So in order to do a quick example, a manufacturer of batteries guarantees that the batteries will last on average 3 years with a standard deviation of 1 year. If 5 of these batteries have lifetimes of 1.9, 2.4, 3.0, 3.5, and 4.2 years, should the manufacturer be convinced that the battery lifetime has a standard deviation of 1 year? And we want to assume battery lifetime follows a normal distribution. And so first we want to find our sample mean and variance. So our sample mean in this case, using our knowledge of how to calculate a sample mean and a sample variance from our formulas discussed in the very first lecture, we would have a sample mean of 3 and a sample variance of 0.815. And so at that point, we can actually go ahead and plug in to our chi-square distribution using our chi-squared statistic formula of the quantity of n minus 1 multiplied by our sample variance divided by our population variance. We would have 5 minus 1 multiplied by 0.815, all divided by 1. And so this would give us a chi-squared value of 3.26. And so therefore this value is from a chi-square distribution. Therefore our degrees of freedom would be 4 because it's n minus 1. 5 minus 1 equals 4. And since our calculated value of 3.26 does in fact lie between the values of 0.484 and 11.143, then we say that the values, which are the values that define the edge of our reasonable range for a chi-square distribution with 4 degrees of freedom, that would tell us that there is no evidence that assuming a population variance of 1 is not an okay thing to do. Again, it's within the range, so therefore we say it's reasonable. If it's outside the range, we assume we have problems. And this range is fully dependent on our sample size. Knowing that this was the example problem I was going to use, I was very comfortable in using that chi-squared distribution with degrees of freedom of 4 to examine our bounds of reasonableness. But that is not always the case for the bounds. To state that a little more clearly, so when we have degrees of freedom equal to 4, the reasonable bounds are between 0.484 and 11.143. That is not the case when we have a different set of degrees of freedom. You need to calculate that anew each time. So for us, this brings us to one of our last points of interest, and that is what happens when our population variance is unknown. Okay, so when the population variance is unknown. So the central limit theorem states that the distribution of our sample mean is approximately normal with mean mu and standard deviation sigma divided by the square root of n. And we know that the central limit theorem is useful for inference about a population mean mu. However, the central limit theorem assumes that the population variance is known. However, we do know that oftentimes we don't have the population variance. So what do we do in that case? Well, what we can do is use something called the t-distribution. And what the t-distribution does is it actually uses the sample variance in place of the population variance. And as such, we are no longer able to use the normal distribution. So we use the t-distribution. The t-distribution is very similar to the normal distribution. It is unimodal, symmetric, and bell-shaped, but it does have more area in the tails than the normal distribution. So if you take a look at the visual to your right, you can see a nice image of our t-distribution and the normal distribution. Sometimes the t-distribution is known as the student's t-distribution. Why it's called the student's t-distribution, I don't know. You can look that up on your own time. Thing about the t-distribution is it is like the chi-square distribution in the fact that it is dependent on the degrees of freedom, n minus 1, which is our sample size minus 1. As our sample size gets larger, the t-distribution does mirror the normal distribution, which is another reason why it is so useful. And this slide is just confirming what I said before, where it is a whole family of distributions characterized by its degrees of freedom. And again, as the degrees of freedom gets larger, it mirrors the standard normal distribution. So for our t-distribution, our t-alpha value will represent the t-value above which we find an area equal to alpha. And since it's symmetric, t of 1 minus alpha is going to be equal to negative t alpha. Why is this important? These shaded regions, these idea of t alpha, these are just a visual representation of those bounds of which we think of things being unusual or not. And we've been kind of playing with this concept of having unusual values in the chi-squared and previous distribution lectures that or topics of this lecture. And so this is just a visual representation of where we find those bounds of unusuality, and it's on the tails. Just as we had with the chi-squared, normal distribution, Poisson, and etc., the t-distribution does have its own table, and it is dependent on that alpha value, which we use to classify our unusuality range, and its degrees of freedom to find our bounds of unusualness. So for a t-distribution with 4 degrees of freedom, that middle 95%, which is where we would say things are most usual to happen, would be between 2.776 and negative 2.776. Again, since it is symmetric, you are going to see just a version of that being positive and negative. So since we have to consider the statistics of our sample mean and our sample variance resulting from taking a sample of size n from a normal population, then in this case, our statistic of interest will be t equals our sample mean minus mu over our sample standard deviation divided by the square root of n. So very similar to what we were looking at with the sampling distribution of our sample mean. And this will follow a t-distribution with degrees of freedom n minus 1. And so if we decide we are going to take a look at a quick example, the average time in minutes that a patient waits to see a doctor at a particular doctor's office is advertised to be 6 minutes. A random sample of 10 patients' wait times were collected and recorded as follows: 5, 11, 9, 5, 10, 15, 6, 10, 5, and 10. If the computed t-value falls between our negative t of 0.025 and t of 0.025, which is just saying that's that middle 95% of our distribution, a prospective new patient will be satisfied with the claim by the doctor's office. And we want to assume that the distribution of wait times to be normally distributed. And just to clarify, so we're assuming, again, our t-distribution is unimodal and symmetric. The doctor is claiming that the wait time is 6 minutes. Now, most people are generally reasonable, and so they know that 6 minutes isn't going to be exact. It might be a little bit less or a little bit more. And this region of acceptability, this is where that negative t 0.025 and positive t 0.025 are. And so if we fall outside of these bounds, then we consider the doctor is making false claims. If it's within that range, then we say, okay, if I had to wait 7 minutes, then I'm saying, okay, yeah, it's 7 minutes, 6 minutes. It's a little bit more, but it's not so much that we'd really care. So first step for this, since we do need to have our sample mean and sample variance, we need to calculate those. So the sample mean in this case would be 8.6, and the sample variance would be 3.306559. That's a longer number to work with than we really want, so we're going to round that to be 3.31. And so now we can go ahead and calculate our variable of t, which remember our formula is t equals our sample mean minus the population mean divided by s divided by the square root of n, plugging in 8.6 minus 6 divided by 3.31 divided by the square root of 10. And we are going to get a t value or t statistic of 2.48. And so we're going to want to compare this to the t distribution with degrees of freedom of 10 minus 1 or 9. And so again, our t value is 2.48, and we are going to try to find our t of 0.025. So here's the 0.025. Our degrees of freedom are 9. And so our bound of interest is 2.262, and we have that as both positive and negative. So our bounds of interest is 2.262, and on the other end is negative 2.262. So this means that if our true mean is 6 minutes, an average of 8.6 minutes is outside the range of values that occurred 95% of the time. And so based on our sample, the prospective patient is wise not to believe the advertised wait time. Okay, so that brings us to the end of our consideration when we don't have the population variance and are instead forced to work with just the sample variance. Sometimes we do like to consider the situation where we're comparing two variances. And when we're in that case, we like to consider the F distribution. This is something that's not a huge focus on in this particular chapter. It is something we'll consider more in chapter 5. But just to give you an idea of what the F distribution is, the F distributions are used when we have two variances of interest. The statistic we use is S1 squared over S2, or excuse me, instead of saying it that way, let's do it another way to make it maybe a little clearer. The sample variance of a first sample divided by the population variance of a first sample over the sample variance of a second sample over the population variance of the second sample. And we say that follows the F distribution with degrees of freedom n minus 1 and n minus, or n1 minus 1 and n2 minus 1. And that's reflective of our two sample sizes since we are considering two samples. And just like the t distribution, the F distribution is different based on the degrees of freedom. And here's a nice visualization giving you an idea of different degrees of freedom and how the distribution can change. So some nice facts about the F distribution. The F distribution is defined only for non-negative values. If you recall, when we are looking at variances and standard deviations, only one of those is non-negative, and that's the one we consider in this case. The F distribution is not symmetric, and there is a different table is needed for each combination of degrees of freedom and also, what kind of significance level we're considering. So in the previous topics of interest, we talked about that bounds of which we consider things to be unusual. And you noticed that we're really talking about that middle 95%, and we said if it went outside those bounds, it was considered unusual. Well, that worked great when we were working with something that was symmetric, but things are a little bit different when it's not symmetric. But again, that's not something we're really going to focus on now, but just be aware that there is a pretty extensive F table that we will be using. And so the decision of which variance to place as the numerator is arbitrary. So notice, as I said, there was this lovely formula, and we are using 2 samples and each of those samples have their own sample variance and population variance. But I do want you to know that although which one you place is technically arbitrary, the F distribution table assumes that the larger variance was placed in the numerator. And in general, as statistic teachers, we do make it the rule of thumb to tell you guys, always put the larger variance in the numerator. And if you're interested in the F table, you can find the table on eCampus. It is several pages long, and I do encourage you to look at it. You're not going to have to do a whole lot of using it at this stage, but that is forthcoming. Okay, so this brings us to the end of this lecture video. Be sure to read Chapter 2, Sections 5 and 6, and finish up Homework 2. I do know that this particular lecture video did have a lot of information that we did cover briefly, so if you have questions, please send me an email, and I'll be happy to answer any questions that you have. Have a good night, everyone.